Hello. This presentation will serve as an introduction to mixed-mode chromatography, which is a technology that was developed here at Silk Technologies. This presentation is going to follow this general structure. First, we will give an introduction to the HPLC instrument itself, followed by an introduction into stationary phases, which are a critical component of the HPLC instrument. And then we'll give an introduction into what mixed-mode chromatography stationary phases are, followed by examples of the different forms that they can come in, which will include cation exchange columns, anion exchange columns, and the Primesep C columns as well. Here we have shown a diagram of a sample HPLC instrument. Up top, you will see that there are bottles of solvent that will compose your mobile phase. The solvents are pumped through tubing into a degasser, wherein any residual gas elements are removed, and then a pump is used to mix your solvents into the different ratios that you've programmed in for your method. The resulting mixture is then pumped into an autosampler, wherein an injection of your mixture of compounds is going to be made. The resulting solution is then pumped through a column, and then depending on the composition of the stationary phase of your column, your analytes in solution may elute all at once or may separate out. And then the resulting fractions are all sent through a detector wherein you acquire data to determine what analytes have separated and which ones haven't. Now down below, we've shown a cross-section of a typical HPLC column. It's a generally cylindrical column that is packed in with your solid stationary phase. And this is where the bulk of this talk is going to be centered upon. And you can think of separating compounds on a column by looking at this picture. This is the Chicago city skyline at the turn of the new year in 2005. And in particular, you should draw your attention to Navy Pier on the lakefront. You want to draw particular attention to the light shown here and think of it as a column. So the light is brightest on the lakefront where the light first hits the water. And then as you move outward from the light source, the light either becomes more faint or perhaps turns into other gradiated fractions. And this is similar to what happens in an HPLC column, wherein a great deal of your sample is concentrated at the start of the column. But depending on the different affinities and intermolecular forces, you see different separation of different components of your mixture as you travel a further distance. HPLC stands for high performance or high pressure liquid chromatography, and it is a method of separation for mixtures that relies on the differing affinities of individual analytes for the stationary phase surface, as well as for the mobile phase that is a liquid that is carrying the analytes through. There are three generally accepted forms of chromatography for HPLC. The first is normal phase chromatography, wherein you are using a polar stationary phase, often coming in the form of silanols, and you are using a mobile phase that is less polar than your stationary phase, and you're separating compounds by their differing polarities. Also popular is reverse phase chromatography. Herein, your stationary phase is now mostly nonpolar, as it is composed of long alkyl chains. And your solvent, that is your stationary phase, is going to be more polar than your stationary phase. The dominant mechanism for separation here are hydrophobic interactions. And one can also use ion exchange chromatography as a separation method. This method separates compounds on their ionic charge and their different degrees of ionic interactions with the stationary phase. As such, your stationary phase can come in two forms, cationic and anionic. With each of the major chromatographic methods, there are secondary phase interactions that one must take into account. With normal phase chromatography, it is possible for the silanol groups themselves to be ionized, and the hydroxyl groups can be ionized to the corresponding oxide ions. These can introduce unwanted ionic exchange interactions. In reverse phase chromatography, there are almost always some number of unprotected silanol groups, as complete alkylation of silanol-based stationary phase is not necessarily possible. And with each of these silanol groups, one can introduce polar or normal phase chromatographic technology, or, as covered above, the silanol groups themselves can be ionized, introducing ion exchange interactions in your reverse phase chromatography. And with ion exchange chromatography, the polymer-based support of your ion exchange stationary phase can actually introduce hydrophobic or pi-pi interactions, similar to that of a reverse phase column. The focus of this talk is going to be on the separation of polar organic compounds, as with each of the three major chromatographic methods we have covered, there are a number of difficulties and limitations. If one were to use reverse phase chromatography with AQ-type columns, they would find that polar organic compounds have an extremely short retention time, that the reverse phase column itself has very limited selectivity for these compounds, and that there is poor reproducibility for each experiment. If one were to try to overcome these limitations by using a reverse phase column and an ion pairing reagent, this would in turn require a complex mobile phase with the ion pairing additives. It requires a dedicated column for each experiment. The resulting eluent from the column is not always compatible with detection methods like MS and ELSD. And this method in general is not compatible with gradient dilution. If one were to do high pH or low pH reverse phase chromatography, wherein one would use high pH for separation of amines or low pH for separation of acids, this approach is limited in that one would only be able to elute one type of compound at a time. Silica-based columns have notably low stability at high pHs and are prone to degradation under those conditions. And there's the potential for poor UV transparency when one is using high pH buffers. Now, if one were to try to separate polar organic compounds with normal phase chromatography, they would once again find limited selectivity for individual components. And there's the potential for a sample solubility problem. As with normal phase chromatography, you are using a nonpolar mobile phase, and polar compounds and nonpolar solvents can sometimes have miscibility conflicts. And if one were to do ion exchange chromatography, this requires charge being present on your molecule. There are only two columns that are available to you, anion exchange and cation exchange. This particular method is not compatible with highly organic mobile phase due to the solubility requirements of the ionic components. And there's a notable poor selectivity towards compounds that may have very different structures, but the same ionic charge. And so, given all of these limitations, I would draw your attention to this graphic down at the bottom of the slide. Herein, we've shown a screw being used to hold a board in place that has a divot in it for a flathead screwdriver. But the tool that one has available to them in this particular circumstance is a crosshead or a Phillips screwdriver. This is a metaphor for using the appropriate tool for the job. And while one could certainly use this crosshead screwdriver to try and tighten this flathead screw into the board, it's not necessarily the best tool for the job, and in fact could cause damage if used too forcefully or inappropriately. And the limitations, as covered on the previous slide, are why there is a necessity for a technology such as mixed-mode stationary phases. Mixed-mode stationary phases are composed of long alkyl chains that are similar to a C18 reverse phase column. However, they differ in that there is an embedded ionized group that can either be negatively or positively charged, located in the middle of the alkyl chain itself. Mixed-mode stationary phases offer several advantages that don't exist with reverse phase columns, including polar compounds being able to be retained by both reverse phase mechanisms and ion exchange mechanisms. Co-eluted compounds can now be separated based on both their hydrophobicity as well as their ionizability or their acidity. Early eluted compounds can be retained using an ion exchange mechanism while also using a highly organic mobile phase. An isocratic method of elution can actually be used for compounds that have very different polarities since all of them are being retained by different mechanisms. And as an added bonus, a single column itself can produce two different mechanisms of separation for the same compound, depending on the mobile phase that's used. This is beneficial because it offers an alternative method of separation, which is sometimes required by the FDA for some pharmaceutical samples. Herein, we have given a summary of the different Primesep columns that we manufacture here at Silk, and we have ranked them by their ionic properties. You can see a sample structure of both types of columns, cation exchange columns and anion exchange columns below. The Primesep C column of the different cation exchange columns possesses the least amount of ionic character. And as one moves along this trend line to the Primesep 200 column, to P, to 100, and then to A, the amount of ionic properties or ion exchange potential is increasing. Similarly, the B4 and B2 Primesep columns possess similar anion exchange character, and as one moves towards the Primesep B column, the degree of anion exchange character is increased. And the degree of ion exchange capacity in each of these columns is determined by switch phase technology, wherein their ionization is changed depending on the pH of the mobile phase. We have given a summary of the different transition points in pH for the different cation exchange columns. And in general, when thinking of the different transition points for the cation exchange columns, wherein the ionizing group is a carboxylic acid, if one is operating at a pH that is below the transition point, the ionizable group will be protonated and be essentially neutralized, and what you'll be working with is a mostly reverse phase column that happens to contain a polar group within it. However, with the cation exchange columns, if one operates above the transition pH, the carboxylic acid is ionized into the corresponding carboxylate, and now the cation exchange column possesses both a reverse phase mechanism from the alkyl chains contained within its structure, as well as ion exchange mechanism from the carboxylate group. Similarly, with the anion exchange column, if one is operating at a pH that is below the transition point, the ionizable group, which for an anion exchange column is an amine group, the amine group will now be protonated into its corresponding ammonium ions. And this particular composition will give you both the reverse phase interaction mechanism from the alkyl chains, as well as an anion exchange mechanism for separation from the cationic ammonium ions. By comparison, if one uses an anion exchange column and operates at a pH above the transition point, the ammonium ions will be deprotonated, and all that one will be left with are the corresponding amine groups. And this column will now operate mostly as a reverse phase column that happens to contain the slightly polar amino group. And now we're going to start going over examples of the different cation exchange columns that are made here at Silk Technologies. This is a general summary slide. Herein, we are separating a three-component mixture of maleic acid, benzonitrile, and benzylamine. We are doing these separations on different cationic and anionic exchange columns. I have ranked them by their different degrees of ion exchange potential. So keep in mind that the Primesep A 100 and 200 columns are cation exchange columns, and the B and B2 columns are anion exchange columns. With the Primesep A column, the maleic acid elutes first. And the reason for this is because it doesn't participate in ion exchange interactions with the stationary phase. And it is also a fairly straightforward molecule that doesn't participate much in hydrophobic interactions with the reverse phase components of the stationary phase. Benzonitrile also does not interact much with the stationary phase, except for its hydrophobic interactions due to the aromatic ring. It also does not participate by an ion exchange mechanism, which is why it elutes second. Benzylamine, though, does participate in an ion exchange mechanism, as the amino group is protonated and converted into an ammonium ion, and thus it is separated on the column by both a hydrophobic mechanism and an ion exchange mechanism, which is why it elutes last on the Primesep A column. Now, if one were to run the same mixture on a Primesep 100 column, they would observe a similar elution pattern. However, the benzylamine would elute at an earlier retention time now, and this is because there is a lessened cation exchange capacity within this column. So the benzylamine elutes earlier. And then if one moves to a cation exchange column with even less ion exchange capacity, like the Primesep 200 column, now you'll note that the benzylamine is actually eluting between the maleic acid and the benzonitrile, which have maintained mostly the same retention times throughout all three of the columns covered thus far. Now, if one were to switch over to the anion exchange columns, now the benzylamine and the maleic acid essentially switch roles. The benzylamine does not participate in anion exchange with these columns, either the B or the B2, which is why it elutes earliest. The benzonitrile is still the neutral compound of the three and elutes at relatively the same retention time as it did in the cation exchange columns. However, the maleic acid is effectively deprotonated and participates in anion exchange with the stationary phases. With the weakly ion exchange capacity holding B2 stationary phase, the maleic acid nearly coelutes with the benzonitrile. And then if one were to use the much more strongly basic Primesep B column, the maleic acid would elute at last from this column and have the longest retention time on the column. By comparison, if one were to take this three-component mixture and attempt to separate it on a standard C18 reverse phase column, they would find that the maleic acid and the benzylamine elute early and at almost the same retention time, while the benzonitrile is retained longest on the column. In this example, we're going to show a separation of different amines on a Primesep A column. All of these amines under this method will be protonated into their corresponding ammonium ions. However, they will also have different retention times in this method. The reason for their different retention times emanates from the different degree of alkyl substitution, as well as what the identity of those alkyl groups are. So for example, ammonia, which is protonated to its corresponding ammonium ion, elutes first from the column, as it does not contain any alkyl substituent groups. Methylamine, or methylammonium, is the second compound to elute, given that it now possesses a single alkyl group. The next corresponding analyte is morpholine, which is now a di-substituted amine. Ethylamine elutes next, and this is because even though it's a monosubstituted amine, it is substituted by a longer chain amine than methylamine or morpholine. Diethylamine elutes next because it does contain the same ethyl group, but it contains two of them. And butylamine elutes last from the column, and this is because even though it is monosubstituted, the alkyl chain is longer in nature, making it such that it can participate more in hydrophobic interactions or reverse phase mechanism with the stationary phase. In this example, we will be showing the separation of the three-component mixture shown down below. It contains the zwitterionic, phenylalanine, the basic, benzylamine, and the acidic, benzoic acid. On the left hand of the slide, we are showing a separation of these three compounds using a standard C18 reverse phase column. In example A, we are separating them using a mobile phase that is 20% acetonitrile and water, and a tetraethylammonium buffered solution that has a pH of 12. Under these conditions, both the phenylalanine and the benzoic acid elute from the column fairly quickly and together. This is because both of their carboxylic acid groups have been converted into the corresponding carboxylate ions, and these ionized compounds do not retain on the column for very long. The benzylamine, however, is not ionized under these conditions and retains longer on the column by the reverse phase mechanism. If one were to switch the mobile phase over to once again using 20% acetonitrile and water and a phosphoric acid buffered solution that has a pH of 2, they would find that the phenylalanine and the benzylamine elute quickly from the column because now their amino groups have been ionized to the corresponding ammonium groups, and the benzoic acid will elute from the column most later because of the reverse phase interaction with the aromatic ring and the compound itself not being ionized. Now, if one were to try to use the mixed mode columns to do this separation, say use the Primesep 100 column and the same phosphoric acid pH 2 mobile phase, they would find that they can separate all three compounds very neatly. The benzoic acid is eluted first under these conditions because it doesn't participate in the ion exchange mechanism and is retained some by the reverse phase mechanism. However, both the phenylalanine and the benzylamine are retained longer on the column and separate neatly from one another. This is because, under these conditions, both of their amino groups are ionized to the corresponding ammonium ions, and they also differ in their retention time by their general net polarities. The phenylalanine contains a carboxylic acid group, which can make it more soluble under the mobile phase conditions than the benzylamine, which is why the phenylalanine elutes before the benzylamine in this method. If one were to also use the Primesep 200 column, and they were to use the same 20% acetonitrile and water, but with an ammonium formate buffer that holds a pH of about 3, they would find that they could manipulate the order of elution. First, the phenylalanine would elute quickly from the column because under these buffered conditions, its zwitterionic nature makes it retain on the column the least. The benzylamine will retain the longest on the column because it will be protonated once again under these conditions. And the benzoic acid will maintain the same retention time as it did in the previous experiment, as the same reverse phase mechanism is retaining it on the column. In this example, we will be showing the separation of different neurotransmitters, shown down below. The dominant property that changes within these neurotransmitters is number 1, the degree of alkyl substitution of their amino groups, and also the count of different hydroxyl or OH groups contained within their structure. This experiment is being conducted on a Primesep 200 column using a TFA buffer. The first compound of these 6 to elute from this column is norepinephrine. The reason for this is because even though it is participating in ion exchange interactions, the 3 different hydroxyl groups it contains interfere with the hydrophobic interactions. When you compare it to epinephrine, which has the same structure but now a dialkylated amino group, epinephrine elutes after norepinephrine, and it is because of the difference in their alkyl substitution of their amino groups. Moving on to the compound dopa. Even though the amino group is once again monosubstituted, one of the three hydroxyl groups has been moved from the benzylic site and is now part of a carboxylic acid. This relocation of the hydroxyl group makes it such that dopa retains longer on the column than either norepinephrine or epinephrine. Then, if one moves over to dopamine, this compound elutes next from the column because it now does not contain a hydroxyl group, and even though it contains a primary amino group, it now only contains two hydroxyl groups. Most notably, these are now phenolic groups. The next compound to elute from this column is tyrosine, and even though tyrosine does now contain a carboxylic acid group, it has removed one of the two phenolic groups that was shown in all of the previous neurotransmitters. This change in molecular polarity and hydrophobicity leads to it being the second to last compound to elute from this column. And then finally, the last compound to elute from this column is phenylalanine. And this is because there are now no phenolic groups on the aromatic ring, which is the key fragment to the hydrophobic interaction. In this example, we are showing the separation of three different polyamino compounds. These compounds differ in structure by the count of amino groups that they have, and subsequently, the number of alkyl chains branching between the different amino groups. If we were to try to separate these three compounds on a standard C18 column, they would all elute as about the same peak or signal. However, if we try to separate these compounds on a Primesep 200 column using a TFA gradient buffer, we would find that these compounds elute in the order that correlates with number 1, the number of amino groups that they contain, and also the number of branching alkyl groups. Both the increased count in the number of ionizable sites, as well as the increase in the number of alkyl chains, increases the retention on the column. It should also be noted that the length of this column, only 10 millimeters, is substantially shorter than that of the reverse phase column, which is 250. In this example, we are showing the effect of the mobile phase on both retention and resolution control of different signals. The 8-component mixture shown down here is a complex mixture of compounds that are acidic in nature, basic in nature, and some that are neutral as well. I will not go over the exact chemical rationalization for the separation of these compounds. Instead, I wish to draw attention to the mobile phase composition. In the top spectra, we are using a fairly diluted mobile phase that is 30% acetonitrile and water, with a TFA buffer that is at a 0.2 concentration. Herein, we see great separation of compounds such as mandelic acid and toluene, while also having quick coelution of peaks such as tyrosine and benzoic acid. However, if we increase the amount of organic modifier in the mobile phase, such that it is now a 70% acetonitrile in water solution, and we subsequently also dilute the TFA in the mobile phase to 0.05, we find that we can change the elution pattern and behavior of the different compounds. Compounds that above were able to elute far from one another, such as mandelic acid and toluene, now elute at very close retention time and as very sharp peaks. However, other compounds that were previously close together, such as the tyrosine and benzoic acid, are now further apart and differ greatly in their interaction with the column. The reason for this is because one controls the hydrophobicity, or the reverse phase interaction, by the organic modifier concentration, and they also control the ion exchange mechanism by the buffer concentration. In this example, we are making use of the Primesep P stationary phase. Primesep P stationary phase is a cation exchange column. However, it differs from other cation exchange columns in that it contains an aromatic ring at the terminus of the alkyl chains. This aromatic ring introduces another interactive exchange in the form of pi stacking interactions. In this example, we are separating two different antiviral drug targets, and the compound that contains aromatic rings, ritonavir, is retained a great deal longer on the column than the compound that does not contain any aromatic rings. And now we're going to begin going over examples of anion exchange columns. In this example, we are separating a mixture of vitamin E and in vitamin E acetate. If one were to try to separate these compounds on a C8 reverse phase column, they would find that the vitamin E elutes first from the column, whereas the vitamin E acetate elutes second. The key reason for this difference in elution is the presence of the phenolic group in vitamin E. This group interferes with hydrophobic interaction. This is partly why the vitamin E acetate elutes second, because the hydroxyl group or phenolic group has been protected by an acetate group. If one were to separate these two compounds on a Primesep B column, they would find that the vitamin E acetate elutes first now, while the vitamin E elutes second. And this is because the phenolic group in the vitamin E participates in ion exchange with the basic Primesep B column, while the vitamin E acetate is only retained on the column via reverse phase or hydrophobic interactions. In this example, we are separating different organic acids on a Primesep B column. These acids differ in three key structural aspects. The first is the number of ionizable sites that they contain. The second is the location of the ionizable sites to one another, most notably in the difference between fumaric and maleic acids, which are cis-trans isomers of one another. And finally, these five compounds differ in their degree of alkyl or aryl substitution. If one were to perform this separation using a mobile phase that is 30% acetonitrile in water using a TFA buffer, they would find that they could separate out these compounds reasonably well. However, there would be somewhat poorer elution of the compounds naphthoic acid and maleic acid. If one were to change the concentration of the acetonitrile to where it is now 40% acetonitrile in water and maintain the same concentration of buffer, they would find that they were able to more cleanly elute the naphthoic and the maleic acids. And this is because changing the solvent concentration changes the hydrophobic interactions. Increasing the amount of organic modifier is going to more quickly elute the naphthoic acid, given that the hydrophobicity has now been modified. In this example, we are going to show the uniqueness of the Primesep B4 column, which is similar to other anion exchange columns, but is composed of a C4 carbon chain, and thus has a different degree of hydrophobic interactions than the Primesep B and B2 stationary phases. In this example, we are separating two different sulfosuccinic acids, one that contains two octyl chains coming off of its structure, and the other that does not. The alkylated sulfosuccinic acid retains on the Primesep B4 column less than the non-alkylated sulfosuccinic acid, and this is because of the greatly reduced degree of hydrophobicity present in the stationary phase. And now we're going to go over the Primesep C columns and some subsequent example applications. Primesep C is named C because the C stands for complex, and it is a stationary phase that forms a weak complex with both amino groups and metal ions. The embedded negatively charged hosting groups interact with amines and other ions, causing unique retention patterns. When separating amines that have equal hydrophobicities on the Primesep C column, the retention order is tertiary, secondary, and primary. And when separating metals on the Primesep C column, the retention order is potassium, sodium, and then lithium. This is unique because it is reverse to what one would usually observe on a standard ion exchange column. And this is an example of separating a four-component mixture, shown here, on a Primesep C column at different pHs of the mobile phase. In the top example, all four compounds have been reasonably separated from one another, and this is because the mobile phase pH is greater than 3.5. As such, the Primesep C column's surface charge is present, and you are able to make use of both a reverse phase and ion exchange mechanism for separation. The analytes also have different ionization states under these conditions. DOPA is in its Zwitter anionic form, which is why it elutes first. Dopamine is in its ammonium ion form, which is why it retains the longest on the column as it's participating in ion exchange with the carboxylate groups. 2-phenylbutyric acid is in its deprotonated carboxylate form, and benzonitrile is neutral under these conditions. This is why these two compounds elute at fairly similar retention times, as they are mainly retained by reverse phase mechanism. By comparison, if one tries to elute the same three compounds at a mobile phase pH that is lower than 3.5, the carboxylate groups have been neutralized and are now just carboxylic acids, and so the only mechanism for separation that one is able to use is dominantly reverse phase. The ionization of the four analytes is also different under these pH conditions. DOPA is now protonated and it is just in its ammonium ion form. Dopamine is still in its ammonium ion form. And the phenylbutyric acid is now protonated and is a neutral polar compound, as benzonitrile is as well. And so this is why the retention order on the Primesep C column is where DOPA in its protonated form now elutes first. Dopamine and benzonitrile co-elute as they are retained reasonably equally due to their relative polarities and hydrophobicities. And phenylbutyric acid is retained the longest as it contains the greatest degree of hydrophobic character of the four different analytes. And for the same experiment, one can actually graphically represent the change in retention time with the buffer pH. On the y-axis, one has the retention time of the different compounds, and on the x-axis, they have the buffer pH itself. Both the benzonitrile and the DOPA maintain about the same retention time in all pH buffers. However, the retention time of the 2-phenylbutyric acid and the dopamine are drastically different and effectively switch places as the pH increases in magnitude. In this example, we are showing the utility of the Primesep C columns for ion separation. The Primesep C column offers a unique selectivity for the retention of alkali ions. Your choice of organic modifier in the mobile phase can change the structure of the complex itself and thus alter the selectivity of the Primesep C column. Alkali metals are retained in the order of potassium, sodium, and lithium, which is reverse to that of classical ion exchange columns. As to the organic modifier chosen, if one were to use acetonitrile as the organic modifier, the ions would elute in the order of potassium, sodium, and lithium. And if one were to use methanol as the organic modifier, they would observe an elution order of lithium, potassium, and sodium. And once again, this is due to the choice of your organic modifier modifying the structure of the complex that forms with the ions themselves. In this example, we are using a Primesep C column to separate 3 different quaternary amines. This is notable because it is otherwise difficult to separate these 3 compounds as they all possess the exact same ionic charge, which was a limitation with ion exchange chromatography. In this case, all 3 compounds do interact with the Primesep C column via cation exchange. However, they are able to elute at different retention times due to their different degree of alkyl substitutions. Tetramethylammonium contains the smallest alkyl groups around it and thus elutes first. Methyl triethylammonium elutes second, as 3 of its 4 methyl groups are now longer in length. And tetraethylammonium elutes last of these 3 compounds, as all of its 4 alkyl groups are longest compared to the other 2. And so, in summary, reverse phase mode chromatography lacks retention of highly polar compounds on conventional stationary phases. This could be overcome by adding different additives to the mobile phase itself, but this introduces its own complexities both in the form of reagent choice as well as column use. These limitations do not exist for the Primesep columns here, which make use of mixed mode stationary phase technology. And so Primesep stationary phases allow for a great degree of flexibility with your different separations, as it gives you multiple vectors of control. And each of these different variables is also compatible with multiple detection methods. And so if we return to the metaphor at the beginning of choosing the appropriate tool for the job, instead of having to use a flathead screw to hold this board in place, one could more appropriately choose a better tool, in this case, the crosshead or Phillips screw that can go more purposefully with the Phillips screwdriver. You need mixed mode columns if you are separating complex mixtures of compounds that have very different properties. You need a method of separation for polar ionizable compounds using a mass spec compatible mobile phase. Gradient elution method is not an option for the separation you're trying to perform. Single mode interaction columns do not significantly select your analytes. You maybe cannot afford to have different individual columns for each individual separation you're attempting. Single mode separation might produce poor peak shape and low efficiency on your method. Or perhaps you just want to save money and time on a difficult analytical situation. These are the different websites you can go to contact Silk Technologies. This is also the address for the company and its phone number. If you contact them, we would be more than happy to answer any questions that you might have concerning any of these products.